Welcome to Fun Facts Online. Today we are abandoning the surface of our planet and diving into the pitch-black abyss of the Mediterranean Sea to investigate a mystery that has shaken the foundations of astrophysics. We are going to talk about a ghost. On February 13th, 2023, something violently energetic tore through the silent darkness roughly 500 meters off the coast of Sicily. It was not a whale, it was not a submarine, and it was not a geological tremor. It was a single subatomic particle. This particle, a neutrino, carried an amount of energy so incomprehensible that it defied the standard catalogs of astrophysical violence. For a fraction of a second, the deep sea was illuminated by a cone of phantom blue light known as Cherenkov radiation. This was the death rattle of a secondary particle created by the collision of a cosmic neutrino with a water molecule. This event has been catalogued as KM3-230,213A. To understand why this is a massive deal, we have to look at the energy involved. This single particle had an estimated energy of 220 Peta-electronvolts, or PeV. In the world of particle physics, 220 PeV is monstrous. It is nearly 30 times the energy of the most powerful record holders previously detected by the famous IceCube observatory in Antarctica. To put this in perspective, 220 PeV is roughly the kinetic energy of a professional tennis ball served at 100 miles per hour. That might not sound like much for a tennis ball, but imagine packing that entire force into a subatomic point with almost no mass. In the scale of the quantum world, this is not a tennis ball, it is a nuclear warhead. Its detection sent shockwaves through the global physics community, triggering a code red hunt across the electromagnetic spectrum. It challenged decades of data from the South Pole and hinted at new physics beyond the standard model. Today, we are telling the story of that particle, the machine that caught it, and the terrifyingly powerful cosmic engine that fired it across the universe. Let us begin with the machine. To catch a ghost, you must build a trap the size of a mountain. Neutrinos are the introverts of the particle zoo. They have no electric charge and nearly zero mass. They are produced in the nuclear fusion of stars, in supernovae, and in the Big Bang itself. Trillions of them pass through your fingertip every second, completely oblivious to your existence. To a neutrino, the Earth is as transparent as a pane of glass. They can travel through a light year of lead without hitting a single atom. However, rarely is not never. If you build a detector large enough, using a transparent medium like ice or water as your target, you can play the odds. Eventually, a neutrino will crash head-on into an atomic nucleus. When it does, it transforms into a charged particle, like a muon, that screams through the medium faster than light can travel in that medium. This creates a sonic boom of light, a blue glow that detectors can see. For over a decade, the undisputed king of this hunt was IceCube, a cubic kilometer of sensors frozen into the Antarctic ice sheet. It had found PeV-scale neutrinos before, with famous events nicknamed Big Bird, Bert, and Ernie, but they topped out around 6 to 10 PeV. This new event marks the entry of a new titan, the KM3 Net Observatory, or Cubic Kilometer Neutrino Telescope. Unlike IceCube, which looks down through the frozen clarity of the South Pole, KM3 Net looks up through the liquid abyss of the Mediterranean. It is currently being constructed in two sites, Orca off France for lower energies, and Arca off the coast of Sicily, designed for the ultra-high energy monsters. When the 220 PeV event occurred, the Arca detector was not even finished. It was operating in a partial configuration known as Arca 21, meaning only 21 of its planned 230 detection strings were active. Each string is a vertical cable anchored to the sea floor, rising 700 meters into the black water, like a reverse kelp forest. Attached to these strings are digital optical modules, pressure-resistant glass spheres the size of beach balls. Inside each sphere is a honeycomb of 31 photomultiplier tubes, looking out into the dark, like the compound eye of an insect. The physics of water gave KM3 a secret weapon. While Antarctic ice is incredibly clear, it is old and pressurized, containing bubbles and dust layers that scatter light. Scattering makes images fuzzy. A sharp track of light becomes a glowing blob. Mediterranean seawater, however, has a much longer scattering length. Light travels in straighter lines. This allows KM3 to reconstruct the direction of an incoming particle with unprecedented angular resolution, less than 0.1 degrees in some cases. On that Monday in February 2023, the Arca 21 detector was simply running its calibration and data-taking routines. The sea was calm, and the background noise from bioluminescent plankton and potassium-40 decay was within normal limits. Then came the muon. The event KM3-230,213A did not look like a typical neutrino interaction. It was a through-going track. When a high-energy muon neutrino hits the water or the rock beneath the detector, it creates a muon. This muon is a heavier cousin of the electron, and because of its mass and speed, it can travel kilometers through rock and water. The muon from this event entered the detector from the side, traveling nearly horizontally. It tore through the instrumented volume, lighting up 1/3 of the entire detector. Over 600 individual photomultipliers triggered in a synchronized cascade. The geometry was the first clue that this was an astrophysical event. Cosmic rays hitting Earth's atmosphere constantly shower us with atmospheric muons. But muons lose energy as they travel through matter. An atmospheric muon cannot penetrate the entire thickness of the Earth. Therefore, detectors usually look down through the Earth to find neutrinos. But this event arrived with a zenith angle of roughly 89.4 degrees, almost perfectly parallel to the sea floor. It had grazed the Earth's crust, traveling through hundreds of kilometers of rock and water before hitting the detector. No atmospheric muon could survive that journey. It had to be a neutrino that interacted close to the detector. Reconstructing the energy of such a particle is like estimating the speed of a jet by the window rattling of a house it passes. The detector measures the amount of light deposited. The muon was glowing with a ferocity Arca had never seen. It was in a continuous radiative regime, shedding energy via breaking radiation and pair production at a rate that blinded the sensors. The algorithms crunched the numbers and found the muon energy was approximately 120 PeV. Since the neutrino gives only about half its energy to the muon, the estimated energy of the parent neutrino was 220 PeV, with a statistical range of 110 to 790 PeV. To understand the magnitude, compare it to the Large Hadron Collider at CERN. The LHC smashes protons at 13.6 Tera-electronvolts. 1 PeV is 1000 TeV. This single neutrino carried 16,000 times more energy than the most powerful collision humanity has ever created. It was a messenger from a universe we can barely imagine, a place where entire stars are shredded and magnetic fields snap like cosmic rubber bands. The publication of the KM3 net result in Nature in February 2025 precipitated a crisis in the field, affectionately known as the Clash of the Titans. IceCube has been running for over a decade, with a full cubic kilometer of ice. It has an effective area much larger than the partial Arca-21 detector. If the universe is filled with 22 OPeV neutrinos, IceCube should have seen dozens of them by now. But it has not. IceCube's record tops out around 10 PeV. When the KM3 net team calculated the flux implied by this single event, it sat awkwardly above the upper limits set by IceCube. This tension suggests three possibilities. First, the cosmic fluke hypothesis. It is possible that 22 OPeV neutrinos are incredibly rare, and IceCube has just been unlucky, while KM3 net got incredibly lucky. This is the winning the lottery on your first ticket scenario. While statistically unlikely, roughly a 0.3% chance, it cannot be ruled out. The second hypothesis is the transient source. IceCube integrates data over years to find a steady glow of neutrinos. But perhaps the universe is not steady. Maybe KM3-230,213A came from a transient event, a sudden explosion that lasted only minutes or hours. If Arca was looking at the right spot at the right time, and IceCube was looking elsewhere, or the Earth was in the way, the discrepancy vanishes. This implies the neutrino did not come from a steady candle, but from a cosmic flashbulb. The third hypothesis is new physics. This is where the theorists get excited. Some theories suggest Lorentz invariance violation, asking if the speed of light still holds as an absolute limit at such extreme energies. Others look at dark matter decay, proposing that super-heavy dark matter particles might decay directly into high-energy neutrinos. If so, this was not an astrophysical accelerator. It was the suicide of a dark matter particle in the halo of our galaxy. So where did it come from? Because of seawater's superior optical properties, KM3 net provided a precise coordinate for the event. The right ascension was 94.3 degrees, and the declination was -7.8 degrees. This points to a region of the sky in the constellations of Monoceros, the Unicorn, and Orion. It is a region rich in galactic history, near the galactic plane, but crucially, no obvious source was there. As soon as the alert went out, telescopes around the world swung to stare at that spot. The Veritas Gamma Ray Observatory looked for high-energy gamma rays and found nothing. The Fermi-Lat Space Telescope checked its archival data for a gamma-ray flare at that time, and found nothing. Radio telescopes listened for the radio afterglow of a relativistic jet and heard only silence. This silence is disturbing. Standard physics says that any accelerator capable of producing a 22 OPeV neutrino must also produce gamma rays. The fact that we saw the neutrino but not the light suggests the source might be opaque to gamma rays. Imagine a black hole wrapped in a thick cocoon of dust and gas. The protons accelerate inside, smash into the gas, and create neutrinos. The neutrinos, being ghosts, fly right through the cocoon. The gamma rays, however, are absorbed by the dust. We see the ghost, but the flashlight is hidden. There is one other suspect, and it is the holy grail of high-energy astrophysics, the cosmogenic neutrino, or GZK neutrino. In 1966, physicists realized that the universe has a speed limit for cosmic rays. If a proton travels through the cosmos with enough energy, it will eventually collide with a photon from the cosmic microwave background, the heat left over from the Big Bang. This collision destroys the cosmic ray, but creates ultra-high-energy neutrinos. KM3-230213A fits the energy profile of a GZK neutrino perfectly. If this is true, it is the first direct evidence of the GZK cutoff in action. However, the flux problem returns. If this was a GZK neutrino, it implies a population of ultra-high-energy cosmic rays so vast that current cosmic ray observatories should have seen more of the parent protons. The detection of KM3-230213A is a Sputnik moment for the KM3-NET project. It proved that the technology works, and it works better than anticipated. Currently, KM3-NET is still expanding. ARCA will eventually grow to 230 strings. As the detector grows, the effective volume will surpass IceCube. We are moving from an era of fishing with a line to trawling with a net. Furthermore, this event creates a mandate for IceCube Gen 2, a proposed expansion of the Antarctic detector that would increase its volume by a factor of 10. To resolve the tension between the North and the South, we need both eyes open. For centuries, astronomy was the study of light. We looked at the universe through the photons that stars were kind enough to send us. But light is fragile. It is blocked by dust, absorbed by gas, and bent by gravity. Neutrinos are different. They are the only particles that can travel from the edge of the visible universe, straight through the heart of a galaxy, through the core of the Earth, and into a detector without deviating. They bring us information from the engines of creation that light can never reveal. The 220 PeV neutrino is a warning shot. It tells us that the universe is capable of violence on a scale we have not fully modeled yet. It tells us that somewhere in the direction of the Unicorn constellation, something accelerated a proton to near light speed, and the only evidence that arrived on Earth was a ghost trapped in a glass bead at the bottom of the sea. The trap is set. The deep sea is listening, and the physicists are waiting for the next ghost to arrive. Thank you for listening to G Fun Facts Online.